All right, so in this virtual lecture, we're going to go over some review problems. I was requested by some students to go over the multiple choice questions on the practice or the sample exam. So I'm going to do that first, and then I will take a couple problems from the other worksheet. I'm not going to go through all of them. I'll just go through go through a sampling. All right, so let me open up. Oh, first of all, I got to share my screen. So hopefully, let's see, share screen. All right, hopefully you can see what I am seeing and you can hear me as well. All right, so let's just go through these one at a time. Um, let's see. All right, so first we want to find the derivative of g of x is equal to square root of x to square root of e all raised to the x power. So the first thing I would do is write this as e to the 1/2 to the x power. And then these powers, when you have a power to a power, you just multiply the powers. So it's 1/2 times x, which is the same thing as x over 2. And then you can see that the derivative in this case is going to be 1/2 e to the x to the 1/2. So I did chain rule. So we have e to the x composed of x to the 1/2 power. So that's, you get that by doing the chain rule. All right, so this next one is a little more complicated. Actually, these next two problems. So we have this table. So hopefully you have the table up and you're referring to what I see. Maybe I can, let's see, can I snapshot this? Let me see if I can. I'm doing all this on the fly, so uh, apologize if there's some kinks. Feel free to skip over the video in any way you feel necessary. So let me see if I can put the table in this right here. Let's see. Yep, here we go. All right, so this is number 2. Again, hopefully you can see all this. So what we want to calculate is, so let's see. Actually, let me make this pen a little bit smaller. Uh, nope, I don't like that. Let's just do, I don't know, brush. Let's see what happens. So it's small. What the heck is going on here? Why isn't this erasing? Whoa. Oh, okay, let's select this. Throw it off. Whoa. Why is that doing that? I don't understand. Hmm. This spot right here is weird. Anyways, I don't know what's happening there. So what we want to calculate is f prime, I'm sorry, f of g prime at 1. So to get this, we first need to use the chain rule, or sorry, the quotient rule, sorry, the product rule. So we have f times g, and we're taking the derivative, and then we're evaluating that at 1. So the product rule states that you take the derivative of the first function times the second plus the first function times the derivative of the second, and we're evaluating this whole thing at 1. And then remember, how do you evaluate this? So first of all, we have this sum of functions, and then of course we have these products right here. So the sum of function is just pointwise. You just evaluate this product at 1 and then this product at 1. So we'll get f prime g at 1 plus f g prime at 1. And then finally we have this product right here, and this product right here. And to evaluate the product, you just evaluate each individual function and then take the product. So it's f prime of 1 times f prime 2, f prime of 1 times g prime of 1, g of 1. And then this will be f of 1 times g prime of 1. All right, now we'll use the table. So to compute this right here. So x is always going to, so we're all evaluating all these functions at x taken to be 1. So we have to just run down this column and look at the corresponding f of x value. So f prime of 1, so that's this row, will be 0. So it'll be 0 times g of 1, which is -1. So times -1, I'm going to put that in parentheses, plus f of 1. So f of 1 is -2. So it's going to be -2 times this last part right here, g prime of 1. So here's our g prime row, and this is g prime of 1, so times 1. And then you can see that this is just going to be -2. All right, so now um, we want to do f over g of prime of 1, or not 1, but -1. So for this, we need the quotient rule. So the quotient rule says you take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So we're taking this whole quotient and then evaluating it at -1. But you can kind of go through the similar steps. So if you evaluate a quotient function at a point, you just evaluate the numerator and denominator at the point. And then, we have this difference here and then products. So you can kind of just evaluate everything and then take a quotient. So this will be the same as f prime of 1, -1 times g of -1 minus f of -1 times g prime of -1 over g of -1 all squared. I don't have the table right. Let's see. So everything's going to -1. So let's see. So f prime negative. So now we're looking at this column. So f prime -1 is 3. So we got, whoa. So we got 3. I'm not going to keep scrolling up. I'll just let you look at the table and I'll read off the values. So we get 3. And then times g of -1, which is going to be 0, I guess, minus f of -1, which is 1, times g prime of -1, which is also 0. So I guess this whole thing is just 0 over g of -1, which is -2. Oh wait, no, I was looking at the wrong column. Sorry. All right, let me read this. So we're going to do f prime of -1, that's 3, times g of -1, that's -2, minus, so we don't get 0 overall, minus f of -1, which is 1, times g prime of -1, which is 0, all over g of -1, which is -2, and that's squared. So we get -6 over 4, which is 3/2, like -3/2. Yep, and that's the right answer. So, oops. All right, so let's do the next one. So we want to compute the derivative of arc cosine of x. And honestly, for this, it's just better to memorize it. So it's going to be equal to -1 over square root of 1 minus x. But if for some reason you forget it, you can actually very easily derive it. So we'll say so this yeah, if you can memorize it, that's the answer. But if you don't remember what this derivative is equal to, you can go through the derivation. It's not that hard. So you let y equal to arc cosine of x. So we want to find y prime, right? We want to find the derivative of this thing here. What's the derivative of this? So now what we'll do though is use implicit differentiation to get this. Uh, so this holds if and only if cosine of y is equal to x. So by implicit differentiation, what do we get? Well, we get we get y prime negative y prime sine of y. That's the so we differentiated this using the chain rule is equal to 1, right? And then that implies that y prime, which is exactly what we want, is equal to 1 over sine of y. So we're not quite done though, because we have y prime and then we have y on this other side. We want it in terms of x. So, but this y is some angle in a right triangle. So let's draw a right triangle. So we have this triangle here. This is angle y, this is 90 degrees. And what we have is that the cosine of the angle is equal to x, which is the same thing as x over 1. But remember, cosine is the same thing as adjacent divided by hypotenuse. So this side we can get by Pythagorean theorem. So we know, so we'll say this side is no, let's say it's I don't know, a, it doesn't matter. We know that a squared plus x squared is equal to 1 squared by the Pythagorean theorem. And so we can solve for a and get square root of 1 minus x squared. So now we now know what this sine of y is. We can compute this y now, right? So using this triangle, so y prime is equal to 1 over sine y, but sine y is equal to, so let's say we just figured out what this a is. Oops, I don't know why it's doing that. That's really weird. This a is equal to square root of 1 minus x squared. So sine is opposite divided by hypotenuse. So sine of y just equals that. Let me actually say well, this implies that sine of y is equal to square root of 1 minus x squared. Oh, don't forget did I put it here or did I drop it? There's this negative. Don't forget the negative. There's a negative here. And so we have negative 1 over square root of 1 minus x squared. So if you're in a bind and you don't remember, so if let me just say this implies that the derivative of our cosine of x is equal to negative 1 over square root of 1 minus x squared. So if you're in a bind and you can't remember this, you can just go through that derivation. Right, so now we want to calculate, so that's done. I guess you put a box. I haven't really been consistent, but I should probably number these, but whatever. So now what we want to, that's not how you spell that. So we want to calculate the derivative of arc tan of theta squared plus 1. Now if you remember arctan, the derivative of arctan, that's great. If you don't, you can go through these exact same steps. So maybe I'll just go through them really quickly. If you don't remember the derivative of arctan, you can get it very quickly. So let y is equal to arctan of x. So that implies that tangent y is equal to x. That's going to be equal to x over 1. So I'm going through the pretty much the same exact derivation, which I need more space. So let me see. Whoa, why is that? I have no idea why that's doing that. All right, this is really weird. Let me start over. Let me close this out. I'll save this. All right, so now if I erase this, will it do that again? Why is it doing that? I have no idea why it's doing that. All right, I don't know why. Anyways, um, I'll just create a new document every time. So we want to, let me just write down what we want to do. We want to calculate the derivative of our tan of theta squared plus 1. And again, you can easily derive the derivative of arctan if you don't remember it. So I'm just going to go through the, whoops, it's tangent of y. For the x, I'm going to go through the exact same steps I just did for the arc cosine. So now I implicitly differentiate this equation right here, and you get y prime is secant squared y, which is equal to 1. And this implies that y prime is 1 over secant squared of y. Remember, secant is it is the sorry, it's 1 over cosine, sorry, 1 over cosine. So this will be cosine squared of y. All right, so now again we gotta y is some angle in a right triangle. So let's draw a triangle to figure out what cosine of y is. So here's our right triangle with angle y. So we have that tangent of y is equal to x over 1, which is opposite or adjacent, right? And then by the Pythagorean theorem, this is the hypotenuse is going to be square root of 1 plus x squared. So this implies, so this part right here you get by Pythagorean theorem. Really, Pythagorean theorem. So this implies that cosine of y is adjacent, so 1 divided by the hypotenuse. So this will be 1 over square root of 1 plus x squared. So hence, we have that y prime, which is cosine squared of y, is this thing squared. So it's going to be 1 over 1 plus x squared. Hence, the derivative of arctan of x is 1 over 1 plus x squared. All right, so that's how you get this derivative if you're in a bind and you can't remember it. So now, let's go back to the problem at hand and compute this derivative right here. So this is going to be chain rule. So we take the derivative of the outside function, which is arctan. So it's this, evaluate it at this inside function. So it's going to be 1 over 1 plus theta squared plus 1 all squared. And then times the derivative of the inside function, which would be 2 theta. And that will be 2 theta over 1 plus theta squared plus 1 all squared. So I guess that's D because you can FOIL this out. So this is kind of a trick problem because it doesn't look like any of the choices. So what you need to do is you need to FOIL this. So you get 1 plus theta to the 4th plus 2 theta squared plus 1. And then you can write this as 2 theta over theta to the 4th plus 2 theta squared plus 2. Okay. So that looks like option D, which is in fact the right option. So that's the end of that. All right, so now what we want to do is we want to simplify cosine of arctan of x. So this is actually not really a calculus problem. This is more of a trig problem. So remember, recall, whoops, that's terrible. Inverse, or let's say the output of an inverse trig function, say arctan of x, is an angle. That's what the inverse trig function gives you. So let's give arctan of x a name. Let's call it, and since it's an angle, we'll use theta because theta is usually used to denote angles. So let this be that. And that, of course, implies that tangent of theta is equal to x, which is x over 1. All right. So now what we want to do is draw a triangle whose angle is theta. This is basically what we've been doing already with the derivations of the derivative of arc cosine and arc tangent. So basically, kind of just reusing those ideas. So all these ideas are really important and they're useful. So it doesn't hurt to know these ideas because you can solve, for example, this problem right here, or you can use these ideas to derive derivatives if you don't remember them. So this is going to be theta. Now we have that tangent of theta is x over 1. So it's opposite over adjacent. And so by the Pythagorean theorem, we know that this is 1 plus x squared, square root of that. So now what we're trying to calculate, or simplify rather, is cosine of arctan of x. Well, we called this theta, so we'll say cosine of theta, and then cosine of theta is going to be the adjacent divided by the hypotenuse. So it's 1 over square root of 1 plus x squared. And that's exactly what we get. That's option A. So that's how you get that option. All right, so now what we want to do is find the linearization. So that's the end of that one. So we want to the linearization of f of x is equal to square root of 2x plus 1. And we want the linearization at 4. So basically, we're just finding the tangent line. So remember that the tangent line gives you the linearization of a function. So remember, that's what it means to be differentiable of a point is that locally that is near that point, the graph just looks like a line. So, all right, so what we need then is a derivative. Well, first of all, let's write this as 2x plus 1 to the 1/2. And then we'll get, well, first of all, I always do this first. I'm always gung-ho and I get a derivative. But let's actually, so we need an equation of tangent line. So we need the slope, which does involve computing the derivative. We also need a point. So let's find that first. Well, we have the x coordinate. So let's get the y coordinate. So it's gonna be square root of, I feel like we did this problem, honestly. Huh. Anyways, so we're gonna get the y coordinate. So square root of 9. That'll be that. So the point, we want the tangent line through this point, 4 comma 3. We have the point. Now we need the slope, which is where finding the derivative comes into play. So the derivative of this function is going to be 1/2 2x plus 1 to the negative 1/2 times the derivative of the inside, which is 2. And so you can rewrite this as follows. Oh, this is a prime. All right, so now we can get the slope at this point. So it'll be 1 over square root of 2 times 4 plus 1. And we basically did this calculation already. It's 1/3. And so the tangent line at 4 comma 3 is going to be y minus the y coordinate, which is 3, is equal to the slope, which is 1/3 times x minus the x coordinate. And then you can write it like this if you want. And you can see that that's option A. So, So the next thing we want to do is find the limit as t equals to 0 of 3t cotangent of 2t. So um remember cotangent of just x is equal to cosine over sine. So as x goes to 0, first of all, the numerator approaches 1, but sine of x gets close to 0. It's a very small number. So you basically have 1 over numbers that are getting smaller and smaller and smaller. So this thing will go off to infinity. So cotangent of x goes to infinity. So the indeterminate form we get is 0 times infinity. So there's, any number of ways we can solve that. Or we could, so we get this indeterminate form and we want to get it into either the indeterminate form 0 over 0 or infinity over infinity. So, and what I was trying to say is that there are any number of ways you can do this. So I guess I would just write it like as follows. So 3t over tangent of 2t. And now you can just note that on the side that you get 0 over 0 now. So you get the proper indeterminate form, and so you can apply L'Hopital's rule. So differentiate the top, you get 3, and then differentiate the bottom. So the derivative of tangent is secant squared. It'll be of 2t times the derivative of the inside function, which is 2. I'm running out of room. Let's see. So now this will be, let me actually put this. So I have 3 halves in the front, and then I have the limit as, oops, t goes to 0 of 1 over secant of 2t. But I mean, you could write it like this if you wanted to add an intermediate step. This is cosine squared of 2t. And this is a continuous function. Cosine is continuous at 0. So you can just evaluate this, and this right here, if you plug 0 into this, you get 1. So the limit is 3 over 2. All right, so now we got 2 more. So let's get through these so I can get on my plane. Right, so now so this is number 9. So again, this is not actually technically a calculus problem. This is more like a pre-calc problem. So we want to basically rewrite the log of square root of arc tan of x all over y x squared. We want to rewrite this using log rules. So first of all, we have this quotient. So this quotient will become a difference. So we arc, yeah, so say square root. Well, actually, I want to write the square root as a 1/2 power. So this would be arctan of x to the 1/2 minus log of y x squared. And then this 1/2 is a power, so it becomes the coefficient like so. And this will be log of arctan of x. And now this is a product, so it becomes a sum, but don't forget there's this negative in the front that you have to distribute over the sum. So it's going to be negative log of y minus log, well, actually, there's this square power here, so it'll be 2 log of x. And so I guess, let's see. I guess the answer is A, which, yeah, that's exactly what we got. So that's that. And then for this last one, we want to find dy dx. So we want to find y prime if y is equal to x minus x, or sorry, x times x minus 1 squared over x minus 3 to the fourth. So you could differentiate this as is. You could use, quotient rule and then product rule and I guess chain rule, but this is a pretty easy application of chain rule. But it would just be easier to use logarithmic differentiation. And in fact, if you do it without logarithmic differentiation, your answer won't look like any of the ones given. So it's kind of a trick problem. Because if you do this log differentiation, the way you do it will be laid out exactly as one of these options is laid out. So what you do is you take the natural log of both sides. This is log differentiation, remember? So the first start of it is to take the log of both sides and then use the log rules to break this logarithm right here down. So we get, if you go through all the steps, you get ln of x plus ln, sorry, you get 2 ln of x minus 1 minus 4 ln of x minus 3. And now we can differentiate both sides. So we get y prime over y is equal to 1 over x plus 2 over x minus 1 minus 4 over x minus 3. And then you get y prime is equal to y times this whole thing. But remember, I'll just plug in the original function of y. So this is y right here. So plug that in. So when you do that, you get x times x minus 1 squared over x minus 3 to the fourth times 1 over x plus 2 over x minus 1 minus 4 over x minus 3. And you can see that this is option E. All right. So now let's go to the sample. Wait, hold on. There's some extra review problems we'll go through. And as I said, I'm not going to go through all of them. So for example, these ones I'm not going to do. You can just use Wolfram alpha to calculate these and check your answer. So let me actually do that. So I'll just give you an example. So here's Wolfram alpha.com. I've mentioned it already before. And so hopefully you've been using it if you've had trouble, because it is useful to check your answers. So for example, if you want to do the first one, well, first try differentiating the problem on your own. So for this first one, you're gonna need chain rule and product rule. And if you do that, let's see what you get. So if you say differentiate e raised to the sine of x, I guess you want to put an asterisk if you want for multiplication times cosine of 4, sorry, times cotangent of 4x. Make sure you have the right number of parentheses, and then you just click enter. There you go, it plots it for you and everything. Yeah, so just go through those on your own and use Wolfram alpha to check. There's actually a website you can use for these. I will go through one of them. Let's say I'll go through this horrible looking one right here. So there's another website, Symbol Lab. Oops. So if you just type in implicit, what the heck is going on here? Type in implicit differentiation of, let's say, the first one. It will do it. Well, actually, what? Oh, this is logarithmic differentiation. Oh, actually, this will actually, well, I'm sorry. Wolfram alpha will be able to do this for you. You can still use Wolfram alpha. I'm thinking about this problem right here. I will do this one, but if you want, this website Symbol Lab can do this for you also. You just type implicit differentiation and then you type the function in. Let's see, there's an implicit one differentiation there as well. All right. Anyways, so let's see. I guess I'll do this one. So this is I'm gonna do this using um logarithmic differentiation. So you take the natural log of both sides. Ugh, maybe I shouldn't have agreed to do this one. This is terrible. 1 to the 8th over sine. Actually, you know what? I'm gonna use paint again because using drawing on this PDF is kind of annoying. So we have so when you take the natural log of both sides, you get ln of e to the sine x times x squared plus 5x plus 1 all to the 8th power over sine of x squared plus e to the x over x squared plus 1 to the 6th. I feel like this is one I added. I don't remember. It's pretty awful though. Oh, sorry, we don't want to differentiate that. Yeah, I'm going to use the log rules to break this up. So we have this fraction, which becomes a difference, and then we have a product here and a product here. So I'm going to just kind of combine a bunch of steps in one. So when you do that, you get ln e to the sine x plus ln. Actually, you have this 8 here, so it's going to be 8 ln of x squared plus 5x plus 1. And then this will be, let me do on another line, minus, because we have this quotient here, ln of sine x squared plus e to the x. We have this product, and we have to distribute this negative over, so it's going to be negative 6 ln of x squared plus 1. And then, oops, sorry, this is ln of y, ln of y. Damn it. Now ln and this e, they cancel because they're inverses of each other, so we get sine of x. And that's pretty much it. You can't really simplify this any further. So let me just write it down again, I guess. And then we'll differentiate. All right, so now when you differentiate this, you get y prime over y, and this will be equal to cosine of x plus 8 times 2x plus 5 over x squared. This is multiply 8 times this fraction plus x squared plus 5x plus 1, and then minus, let me do it again on the next line, minus the derivative of this. So the derivative of, it'll be the derivative of this over itself. So we had to use the chain rule first. So the derivative of this will be equal to cosine of x squared plus e to the x times the derivative of the inside, which oof, that's kind of bad notation, times 2x plus e to the x, and that's going to be over sine x squared plus e to the x, and that'll be minus 6 times 2x over x squared plus 1. And then we can write this. Now we'll multiply both sides by y. But y, remember, is, oh God, it's really awful. It's going to be e to the x, or sorry, e to the sine x, x squared plus 5x plus 1 to the 8th power over sine of x squared plus e to the x times x squared plus 1 to the 6th. And then it's going to be times all of this mess right here. So it'd be cosine of x plus, say 8 2x plus 5 over x squared plus 5x plus 1. This is terrible, man. And then minus, so we have sine, cosine over sine, so this would be cotangent. It will be cotangent, but then there's this thing I'm going to put in the front, so it'll be 2 minus 2x plus e to the x times cotangent of x squared plus e to the x. And then this will be minus 12x over x squared plus 1, parentheses. So it's this whole thing times this thing which I had to write in on 2 lines. So hopefully that makes some sense. All right, so this next one is a implicit differentiation problem that I will go over. So this is number 3A. So we have this equation y to the sine x is equal to x cosine of y. I guess we'll put parentheses here. And we want to differentiate this implicitly and then find the tangent line at negative pi. So the first thing I would do, so I have y to this power, it's kind of awful. What I would do is I'd take the natural log of both sides to get rid of that. And then use the log rules to write it as sine x times ln of y is equal to ln x plus ln. Sorry, this is terrible looking. It should be ln of x, like parentheses, I guess. I don't know. Plus ln of cosine y. And now I will differentiate this. So I got to do product rule here. This will be chain rule. So on the left-hand side, what we'll have is cosine of x times ln of y plus sine x times y prime over y is equal to 1 over x plus negative sine y times y prime over cosine of y. So we'll write this as cosine x plus ln, times y, ln y plus y prime over y times sine x is equal to 1 over x. This will be minus y prime times tangent y. So I have this y prime here and y prime there, so I need to put these together and solve. So I'll add this thing to both sides, and then I'll subtract this from both sides. So you get y prime over y sine of x plus y prime tangent of y is equal to 1 over x minus cosine x times ln of y. And then you factor out y prime, you get sine x over y plus tangent of y is equal to 1 over x minus cosine of x times ln of y. All right, and now we can divide by this, so you get y prime is equal to 1 over x minus cosine x times ln of y over sine of x over y plus tangent of y. So I guess what we'll do, since we have this y here and this x here, multiply the top and the bottom, just to make it a little cleaner. It's not strictly necessary, but I'll multiply the top and bottom by x times y. So what you get is y minus xy cosine of x times ln of y in the numerator, and then you get x sine x plus xy tangent of y. So let me plug this into Symbol Lab, see if this is right. Let's see if we did this right. Oops. Oh, so we want to do implicit differentiation of y raised to the sine x is equal to x cosine of y. Let's see if I can figure this one out. Hmm. It's a little different. I mean, it looks mostly right, but I don't know why this is looking like this. Hmm. I don't know. I think ours is right. I guess maybe Symbol Lab is maybe it's having issues or something. Yeah, I mean it is hit or miss sometimes. Um, using Symbol Lab and Wolfram Alpha. So I guess it's good that I went through this because maybe you would if you type this in and you might have been confused. So yeah, it's a little different. I don't know why. Anyways, um, I'm pretty certain that what I did was right, so we'll just stick with that. So now we have y prime, and now we want to evaluate at when x is equal to negative pi, and then y is equal to pi to get the slope of the tangent line. So what we'll have is pi. Oof, this is terrible. Okay. Time minus negative pi times pi times cosine of pi times ln of pi over oh, interesting. Okay, so times pi sine of pi. Well, that's going to be 0. And this other thing's going to be 0. So actually, I don't think you have a tangent line. There, let's see. So pi. Wait, so sorry, this is, it's not going to make a difference, but this is negative pi sine of negative pi. That's still 0 plus negative pi tangent of pi. So this right here is equal to 0. This right here is equal to 0. So we should have a vertical no tangent line, or maybe we'll say vertical tangent at this because y prime is not defined at the point. So let's actually plot this equation. We should be able to. So in other words, we have a vertical tangent at this point. So I don't know if we can see it or not, but so we want to plot. Let's see, plot y raised to the sine x is equal to x cosine of y. So we want to plot it near negative pi. So let's say um, negative. So we want to say maybe x is from negative 5 to 4, negative 4. I don't know if this will work actually. If it will let us plot on that small interval. Yeah, I don't think it knows. Doesn't know what I mean. That's all right. Let's go back to the original graph. Oh wait, I think it did work actually. So this is like right here, this point right here is roughly negative pi. And it's yeah, the graph is kind of crazy right here. It like oscillates. I guess it's reasonable that there's some sort of vertical tangent. So I guess that means we did something right. So, but let me try plotting it from -5 to -4 again. See what happens. So it actually looked like it worked. Oh wait, I just plotted the wrong function. This should be cosine. Nope, doesn't know what I'm doing. All right, but I actually originally plotted the wrong thing. So let me get rid of that. Let me just do plot this equation. All right, I guess maybe so let's see. Can I plot a point? Negative pi, comma pi. Now I'm not sure. This I think what we did was right, but I don't know if it'll let me plot an individual point. I was thinking this point right here. So at this point right here, we have a vertical tangent, but that wouldn't be at pi. So that's too high. It's close to 10. So like -3.5 is like 3.71 or whatever pi is. It's like right here, maybe. This is one, two, three, four, five. So this is four. Well, this is so maybe like right here. So if you trace it up, so it does actually look like it has a vertical. I mean, it doesn't have a vertical tangent line. So I'm not sure what happened. Hmm. Sorry, this was not scripted. I was been super busy this weekend, and like I said, I had to fly in a bit, so trying to squeeze this in. Uh, Anyways, let me move on to some other problems, and if something occurs to me, maybe I'll go back to it. Of course, alternatively, you can go to the tutoring room. I'm sure someone there can help you with this. All right, let's see. Or maybe I should do some more problem. Let's see. All right, well, how about we do this diagonal cube problem? I guess I could try it, but I might screw up the diagram. So we have basically this is the cube problem. So we have, let me see if I can draw a cube. I don't think so. Actually, I can do it like this. Something like that, maybe. And you connect these. It's not look exactly like a cube, but that's right. That's kind of terrible. But anyways, um, so this is a cube, so all the sides are x, and we're told that dx dt is changing at a rate of 2 centimeters. The instantaneous rate of change of x is 2 centimeters per second. And then we want to know about the diagonal. So like there's like yeah, I use different color. So I mean there are lots of different diagonals, but for example, you have a diagonal from here to crap out there, like here. So now you can actually just get this what this is using the Pythagorean theorem, what the length of the diagonal is in terms of these x's. So what you have, like we can extract this triangle here. Let's see. So you definitely have that this one side is x. Oh, and then this is, yeah, this will be 90 degrees. And so what we want is the diagonal is this hypotenuse here, but I don't know how to, well, we know that maybe we know this angle here. Oh, no, that shouldn't be 45 degrees. That should be, hmm, let me see. Oops. All right, maybe let me pause this for a second. So let me stop my sharing and pause this for a second. All right, I think I figured it out. So let me share my screen again. All right, so here we go. This is the sort of setup that we have. And this line, so this, let me see. Let me just scratch that. So I want to extract this one triangle. So this line I drew right here, L, call it L. This is the diagonal, the length of it, and we want to figure that out. And then we have this dotted line, and then we have this X right here, 90 degrees. The problem I was having was I don't know how to compute this dotted line. So we'll call this, let's say A. So we actually have kind of two unknowns. This side right here, we definitely know this is X, but this side is actually not that bad because this side A, this dotted line I drew here, is the diagonal of the bottom face. But the bottom face is just a square. So we want to find out what L is in terms of X. So let me now extract the bottom face. The bottom face is just this square. Let me use black. Oops. So here's this bottom face. And then what we have is we're looking at that dotted line. So we're looking at this thing from like 2 dimensions, I guess, like looking straight down at it. And we know this is A right here. We want to find A first, because once we find A, then we can find L in terms of X. So, and we know that these sides right here are X, and then this right here is a right triangle. So what we have, oh, this side's X also, all of the sides are X. So we have by the Pythagorean theorem, this is a pretty good problem. We have that the hypotenuse A squared, which is actually usually C. Sorry about that, but hopefully that's not confusing. Hypotenuse is the squares of the legs, the sides added together, right? So now A is going to be equal to square root of 2. Maybe I'll say X square root of 2. Uh-oh, I am out of room. That sucks. All right, so now we know that this right here is X square root of 2. And so now again, by the Pythagorean theorem, we can figure out what L is now. So L squared, because now L is the hypotenuse of this other triangle right here, L squared is going to be equal to X squared plus A squared, but this is A right here. We found that out. So this will be X squared plus 2X squared, which will be 3X squared. And so then this implies that L is equal to square X times square root of 3. All right, now what we want, so this is what we have, right? Sorry, we didn't start with what we have. What we want is dl dt. What is this equal to when, let me pull up the problem. Actually, you don't need specify an x. We just want to find out what is the rate at which the diagonal is changing. That's okay. So now what we can do is just differentiate this right here. We have dl dt is equal to, let's say root 3 times dx dt. And now we know dx dt is 2 centimeters per second. So this would be 2 root 3 centimeters per second. A little messy, sorry about that, but that's how you solve that. So hopefully that makes some sense. All right, let's see. Maybe I'll do 2 more problems. All right, so let me open this up again right here. So we have these derivatives and we want to find out some geometric information about the function from these derivatives. So we're given this function right here and then its derivatives. So first of all, where's it increasing and decreasing? So that you get by the first derivative. So note that e to the 2x is always positive. So this factor right here completely determines the sign. So it's the first derivative is positive when 2x plus 1 is positive. And so that implies that x is bigger than negative 1/2. And then in interval notation, that will just be negative 1/2 to well, it's negative 1/2 to infinity. So when 2x plus 1 is positive, the first derivative is positive, hence it's increasing on that interval. And then it's decreasing when 2x plus 1 is negative, which is equivalent to saying x is less than negative 1/2. And so now the interval on which we're decreasing is negative infinity to negative 1/2. All right, local minimum. So this implies that x equals negative 1/2 is a critical point. Well, we actually can see that if you plug in negative 1/2, it does make the derivative 0. So this is definitely a critical point. And so we just need to figure out, is it a minimum or a maximum? So if you notice, what this says is that this is to the left of negative 1/2, we're decreasing, and then to the right of negative 1/2, we're increasing. So decreasing to increasing means we have a local minimum. So there's no maximum. I should say no local maximum, but there is a minimum, and there will be a local minimum, and it will be at negative 1/2. So let's plug in negative 1/2. So we have negative 1/2 e to the 2 times negative 1/2, and that'll just be negative 1/2 e. So at the critical point 1/2, we have a local minimum, and the point corresponding to it is negative 1/2 comma 1/2 negative 1/2 times e. All right, so for concavity, we need to look to the second derivative. Again, this e to the 2x is always positive, and of course 4 is always positive. So the sign is completely determined by this x plus 1. So when x plus 1 is bigger than 0, which is the same thing as saying x is bigger than negative 1, we are concave up. So the second derivative will be positive. So we're concave up on the interval negative 1 to infinity. And then concave, the second derivative will be negative when x plus 1 is negative, which is the same thing as saying x is less than negative 1 And so we're concave down on the interval from negative infinity to -1. So the concavity changes at x equals -1. So we could say that that there's an inflection point at -1, and we can plug it into the function to figure out what the y coordinate is. So the actual inflection point will be -1, comma, negative e to the -2. All right, let's see. So we've done a million curve sketching problems. So I don't want to really do those, but this one is all right. So this one is just, I won't go over this one because it's just um find the derivatives and then observe where it's increasing or decreasing. You can actually, Wolfram Alpha can also do this. So I'll let you do that on your own. Let's see here. These are pretty straightforward also. You should be able to, Alpha should be able to help you with those as well. Let's see. And yeah, we've done a million of these already, so I'll let you do that. I guess that's good enough. I had to get going anyway, so hopefully that helped. So that was just I just did a yeah. Anyways, I gotta go. So sorry.